Now let's look at the root test. The root test is very similar to the ratio test, and the biggest difference is that we're computing a limit now that looks a little different. It's the limit as n goes to infinity of the nth root of an. So it looks at the nth root of the terms of our series in absolute value. And taking the limit as n goes to infinity, again we have the same conclusion that we had before. If that limit comes out to be something that's less than 1, then the series is absolutely convergent. If the limit comes out to be something that's greater than 1, then the series is divergent. And if the limit comes out to be something that's equal to 1, then the ratio test is inconclusive, just like before. Okay. Now let's try it out in an example. Notice that the thing that will make the root test useful will be the cases that simplify nicely when we apply an nth root. So if your series has terms with powers of n on them, we know that they'll simplify nicely with the nth root. Take, for instance, here we've got the series 2n plus 3 over 3n plus 2 all raised to the power of n. So this is clearly one that will simplify nicely when I apply an nth root to the terms. So let's see what happens here when I take the limit as n goes to infinity of the nth root of the absolute value, 2n plus 3 over 3n plus 2 to the power of n. So clearly here we can just cancel out the nth root with the power of n. So we're just left with the limit as n goes to infinity of 2n plus 3 over 3n plus 2, which is now an easy limit to evaluate. For instance, here, if I just divide out the factor of n from the top and the bottom, (2 plus 3 over n and 3 plus 2 over n, we notice that the remaining terms, 3 over n, 2 over n, both go to 0. So our limit here is 2 over 3. And since this comes out to be something less than 1, we know it's convergent by the root test. Okay, so it's a pretty straightforward variation of what we saw with the ratio test. Just taking that limit and evaluating the limit. If it comes out to be something less than 1, we know it's convergent. If it comes out to be something greater than 1, then we know it's divergent. If it comes out equal to 1, that's the case that we have to be careful with. We should try and avoid those cases with the root test if we can. So notes on the root test. The root test works best for series involving expressions of the form f of n to the power of n. So if we have a power of n on the terms of the series, then that's a good indicator that the root test would be a good choice. We know that the limit that is obtained from the root test is usually equivalent to the limit obtained by the ratio test. In other words, the root test and the ratio test, if I apply either method, should yield the same limit, or the same value as L. And the following limit may be helpful when applying the root test. So if I'm taking the limit as n goes to infinity and I get an expression of the form square root of n over n to the p, the nth root of n to the p, notice that this is going to be an indeterminate form, or an indeterminate power, because here if I were to rewrite this, this would be n to the p over n power. So this is in the infinity to the power of 0 form. So it's one of those indeterminate forms. So what I could do is just rewrite it in a form where I can use L'Hopital's rule. I'll write e to the ln of n times p over n, which now is in the form p times ln of n over n, and now it's in the the infinity over infinity form. So when I apply L'Hopital's rule, I get p times 1 over n over 1, and now as n goes to infinity, this goes to 0. So it's equal to 1. So that might be helpful just to know this, right? That if I see things like, the limit as n goes to infinity, the square root of, or the nth root of n, we know this is just equal to 1.